The first example where we're going to see a breakdown is anytime we have an odd number of valence electrons. This is probably the easiest to explain and to think about, because if we have an odd number, that means that we can't have our octet rule, because our octet rule works by pairing electrons. And if we have an odd number, we automatically have an odd electron out. So if we look at an example, the methyl radical, we can first think about how we would draw the Lewis structure. We draw the skeletal structure here. And then what we're going to do is add up our valence electrons. We have 3 times 1 for the hydrogen atoms. Carbon has 4 valence electrons, so we have a total of 7. If we want to fill all of our valence shells in each of these atoms, we're going to need a total of 14 electrons. So what we see we're left with is that we have 7 bonding electrons. So we can fill in 6 of those straightforward here, because we know that we need to make 3 different bonds. And now we're left over with 1 electron. We can't make a bond. So what we'll do is carbon does not have an octet yet. We can't get it one, but we can do the best we can and help it out with adding that extra electron onto the carbon atom, so that at least we're getting as close as possible to filling our octets. This is what we call a radical species, or a free radical. Free radical or radical species is essentially any type of a molecule that has this unpaired electron on one of the atoms. This might look really strange. We're used to seeing octets, but you'll realize if you calculate the formal charge on this molecule that it's not the worst situation ever for carbon. At least its formal charge is 0. Even if it doesn't have, it would rather have an extra bond and have a full octet. But it's not the worst scenario that we can imagine. But still, radicals tend to be incredibly reactive because they do want to fill that octet. So what happens when you have a radical is it tends to react with the first thing that it runs into, especially highly reactive radicals that are not stabilized in some other way, which you'll tend to talk about in organic chemistry, how you can stabilize radicals. So the term free radical should sound familiar to you, whether you've heard it in chemistry before or you haven't heard it in chemistry, but maybe have heard it in, I don't know, commercials for facial products or other things. People like to talk about free radicals, and they're sort of the hero that gets rid of free radicals, which are antioxidants. So you hear in a lot of different creams or products or vitamins that they have antioxidants in them which get rid of free radicals. The reason you would want to get rid of free radicals is that free radicals can damage DNA. So they're incredibly reactive. It makes sense that if they hit a strand of DNA, they're going to react with the DNA. You end up breaking the strands of DNA and causing DNA damage. So this is actually what happens in aging, because we have a lot of free radicals in our body. We can introduce them artificially. For example, cigarette smoke has a lot of really dangerous free radicals that get into the cells in your lungs, which damage your lung DNA, which can cause lung cancer. But also, all of us are living and breathing, which means we're having metabolism go on in our body, which means that as we use oxygen and as we metabolize our food, we are actually producing free radicals as well. So it's kind of a paradox, because we need them because they are a natural byproduct of these important processes, but then they can go on and damage cells, which is what kind of is causing aging and can lead to cancer. We have enzymes in our body that repair damage that is done by free radicals that will put the strands of DNA back together, and we also have antioxidants in our body. So you might know that, for example, very brightly colored fruit is full of antioxidants. They're full of chemicals that will neutralize free radicals. Lots of vitamins are also antioxidants. So we have vitamin A on the top there and vitamin E. So the most common thing we think of when we think of free radicals is very reactive, bad for your body, causes DNA damage. But the reality is that free radicals are also essential for life. So this is kind of interesting to think about. And for example, certain enzymes or proteins actually use free radicals in order to carry out the reactions that they carry out in your body. So for example, this is a picture or a snapshot of a protein. This is a crystal structure of ribonucleotide reductase is what it's called. It's an enzyme that that catalyzes the reaction of an essential step in both DNA synthesis and also DNA repair, and it requires having radicals within its active site in order to carry out the chemistry. So this is kind of a neat paradox because radicals damage DNA, but in order to repair your DNA, you need certain enzymes, and those enzymes require different types of free radicals. So free radicals are definitely very interesting, and once we get, or hopefully you will get into organic chemistry at some point and get to really think about what they do in terms of a radical mechanism.